All right, let's look at one more example similar to the one we just did in the previous video. So before I do anything for a rational function, I'm going to factor the numerator and denominator just to make sure there's no holes of any type occurring. So if I factor the numerator, that's I guess x plus 5, x minus 1. And if I factor the denominator, I guess that's x plus 2 and x minus 1. And again, notice, always factor your rational function first, because things like this may happen. That means x equals 1 is not vertical asymptote because I can cancel it out. So I'm going to cancel this out, and I'm going to focus on x plus 5 over x minus 2 as my new function, with the added idea that x cannot equal 1. I'll take care of that at the end. There's going to be a hole there. But right now, I'm essentially looking at this. This is the new function I'm going to graph. I'm going to focus on that. So VA, x is equal to -2, because I'm just going directly to the bottom of that new yellow function and setting it equal to 0. Horizontal asymptote, since the numerator has a degree 1 and a denominator has a degree 1, I just take the coefficient 1 and divide it by 1. So 1 over 1 is just y equals 1 for my horizontal asymptote. For my x-intercept, I'm going to make the numerator equal to 0. And in my yellow function, x plus 5 equals 0 gives me x equals -5. So my x-intercept is -5, 0. For my y-intercept, I'm going to make y 0. So that's going to be y equals, or x equals 0. So that's going to be y equals 0 plus 5 over 0 plus 2, which is just 5/2. So my y-intercept is 0, 5/2, or 0, 2.5. So with those tools, we're going to go quickly sketch this thing. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We got one vertical asymptote at -2. We got a horizontal asymptote at +1. We got an x-intercept of -5. So I guess I'll go over here. 1, 2, 3, 4, -5. And we got a y-intercept of 2.5. So 1, 2, 2.5. All right, so with the tools that I recall from, I just use this dot and I get closer and closer to the VA, and I use this dot and I get closer and closer to the HA. And similarly, I use this dot and I get closer and closer to the HA and closer to the VA. So that's what my graph looks like. However, remember we said that initially, don't ever forget about that because that's a common mistake, forgetting about the hole. Initially, we got rid of x equals x minus 1 factor, which caused us to create this new yellow function, but we know x can't be 1. So I need to go find, when x is equal to 1, this new function that I made, where does the hole happen exactly? So when x is 1, I put that in, and I guess I get 6 over 3, which is 2. So the hole happens at 1, 2, assuming I've made an accurate graph. And I guess that is fairly accurate. At 1, my graph goes through 2, but there's a hole that I should make there. So common mistake is forgetting about that hole in your last step. So always, always, always factor your rational function. If things cancel out, remember you're going to have holes at the end of your problem. Domain. All right, we're going to say x such that x can't equal to the VA, which was -2, and also x can't equal 1, the hole that we just put there. And for the range, y such that, I guess everything is okay for the range except this y equals 1, that's a border, so y cannot be equal to 1. And I also have to pay attention that not only that, we forgot about this hole for the range. Y also cannot be 2, where I made the hole. So y cannot be 1 because of the horizontal asymptote, and y cannot be 2 because of the hole that I just made. All right, let's go to the last example. And the rational function is already given to us. This is number 88 from your text. It says, after a certain drug is injected into the patient, the concentration C of the drug in the bloodstream is monitored. At time t, of course time greater than 0 in minutes, the injection concentration is given in these units by this function. So t, the input is minutes, time, and C, or C of t, is, I guess, the concentration of the drug in your body. The level of it in milligrams per liter. Draw a graph of the drug concentration. So we're going to use our TI to go look at this, because it says a TI calculator required for this problem. And then tell us, part B says, what eventually happens to the concentration of the drug in the bloodstream. So let's go put this into our TI. So I have 30x over the quantity x squared plus 2 on there. And if I do a zoom 6, it looks like I could use a better window. So I'm going to go to window. And since time is positive, I'm only going to worry about quadrant 1. So x min, I'll put 0. X max, let's go for like 20 minutes, see what window we get. And then y min, I'm going to put 0. And y maximum, let's go up to like 20 also, see if we get a better graph. Now I'm going to push graph. And yep, that definitely looks better. So it looks like the concentration starts at 0, goes up, reaches a peak, a maximum, and then it slowly becomes lower and lower and lower. And if we were to look at this, and if I go to window and walk all the way to the right, let's make the x max like 50. Notice what happens is it gets lower and lower, closer to the x-axis. And if I go to window again and go to like 100, let's say 100 minutes later, and I push graph, it gets closer and closer to the x-axis, but never crosses it because that's actually a horizontal asymptote. So for the graph, we basically had something like that happen. And eventually, what happens to the concentration in the bloodstream, we'll say as t goes to infinity, C of t, or C, approaches 0 in this case. Because if you look at the degree of the numerator here, t to the 1, and the degree of the denominator here is t squared, since the numerator degree is smaller than the denominator, our HA in this problem is y equals 0, therefore indicating that as I walk over to the right, the concentration approaches 0. So eventually, as time goes by, the concentration in the body goes to 0, and since it never touches the horizontal asymptote, as you go to the right, it's saying technically you're always going to have small traces of it in your body.